Tonight, we are going to talk about a number, not a famous number, not pi, not the speed of light, not any number you have ever heard about in a science class or seen on a poster. This is a number that most people have never heard of, and yet it might be the most important number in the entire universe. Because if this number were slightly different, even by an almost immeasurably tiny amount, you would not exist. Every star in every galaxy across every corner of the observable universe would not exist. There would be nothing, no matter, no structure, just an expanding ocean of radiation, growing thinner and colder until the universe reached a kind of featureless equilibrium and stayed there forever. The number is the mass of the Higgs boson. And the problem with the Higgs boson's mass is not that it is wrong. It is that it is exactly right, and nobody knows why. That might sound like a good problem to have, a particle with exactly the right mass. What is the issue? The issue is that when physicists sit down and calculate what the Higgs boson's mass should be, based on everything else we know about how the universe works at the most fundamental level, the answer they get is not 125 billion electron volts. The answer they get is roughly 10 million billion times larger than that. The Higgs boson should be almost incomprehensibly heavier than it actually is. The mathematics of our best theory of reality screams that this particle should be 1 trillion times more massive than what we observe. And yet it is not. It is light. Extraordinarily, suspiciously, almost impossibly light, and no one can explain why. This is called the hierarchy problem, and it is one of the deepest cracks in the foundation of modern physics. Not a crack in the sense that something is broken, our equations still work, our predictions still match experiments with breathtaking precision, but a crack in the sense that something is missing, something deep, something we have not yet found. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now make yourself comfortable. Let us begin. To understand why the Higgs boson's mass is such a profound mystery, you first need to understand what the Higgs boson actually is. Not in the vague popular science way you may have encountered it, the so-called God particle, the thing that gives everything its mass. That framing, while dramatic, leaves out what is actually extraordinary about it. To really grasp the problem, you need to understand the machinery the Higgs boson is part of, the mechanism it enables, the role it plays in the architecture of reality. So let us start from the beginning. Let us start with what the universe is actually made of. Everything you have ever touched, seen, or interacted with is made of a small number of fundamental particles. These particles have no internal structure. They are not made of anything smaller. They are, as far as we can currently determine, the bottom of the ladder, the most basic units of matter and energy that nature uses to build everything else. Physicists have spent over a century cataloging these particles and figuring out how they interact. The result of that effort is what they call the Standard Model of particle physics. The Standard Model is arguably the most successful scientific theory ever constructed. It predicts the behavior of subatomic particles with a precision that no other theory in any field of science has ever matched. When theorists calculate something using the Standard Model and experimentalists go measure it in a laboratory, the numbers agree. Not roughly, not approximately. They agree to 11 decimal places. That is not a typo. 11 decimal places. If you wanted to predict the distance from New York to Los Angeles with that degree of accuracy, your answer would be correct to within a fraction of the width of a single atom. And yet physicists are almost certain the Standard Model is not the final theory of reality. Not because it fails in any domain where it has been tested, it does not, but because it is incomplete. There are things it cannot explain. Entire categories of phenomena it simply does not address. And one of the most pressing problems with the Standard Model involves the particle that was supposed to complete it, the Higgs boson. Finding the Higgs boson was supposed to be the triumphant closing chapter of a 50-year quest, and in some ways it was. When scientists at the Large Hadron Collider announced its discovery on the 4th of July, 2012, it was a genuine moment of scientific triumph. Peter Higgs, the physicist who had predicted the particle's existence nearly 50 years earlier, sat in the audience and wept. Thousands of physicists around the world had spent decades building the machines and running the experiments that led to that moment. But as the celebrations faded and physicists began to study the Higgs boson in detail, they confronted a problem they had known was waiting for them. A problem that the discovery of the Higgs, far from solving, made impossible to ignore any longer. The Higgs boson is not just a particle, it is a symptom. And what it is a symptom of is a deeper tension in our understanding of reality, a tension between what our best theory says should be true and what actually is true. A tension that suggests something is out there, beyond the Standard Model, beyond everything we currently know, waiting to be discovered. That something is what we are going to talk about tonight. We are going to go deep into the Higgs boson, deeper than almost any popular account has gone. We are going to understand not just what it is, but why its very existence poses one of the greatest intellectual challenges in all of modern physics. We are going to walk through the hierarchy problem, slowly and carefully, until you genuinely understand why physicists find it so disturbing. We are going to explore the solutions that have been proposed: supersymmetry, extra dimensions, composite models, fine-tuning, and examine, honestly, why none of them are entirely satisfying. And we are going to ask what it means that the most powerful particle accelerator ever built has found no explanation for the Higgs mass, despite everyone's expectation that it would. By the end of tonight, you will understand why the particle that completed the Standard Model might also be the thing that breaks it, and why that breaking might be the most important thing that has happened in physics in a generation. Let us begin. Before we can understand what the Higgs boson is and why its mass is so troubling, we need to understand the world it lives in. Think about the last solid object you touched: a table, a wall, a coffee mug. It felt solid, didn't it? Continuous, dense, the kind of thing that stops your hand when you push on it. Now zoom in past the surface, past the molecules of wood or ceramic or glass, past the atoms that make up those molecules. Keep zooming. You have reached the nucleus of an atom, now a tiny, incredibly dense cluster of protons and neutrons packed tightly together. The nucleus is real. It is there. But around it, almost nothing. The electrons that orbit this nucleus are so far away relative to the nucleus's size that if you blew up an atom to the size of a football stadium, the nucleus would be a marble at the 50-yard line. The electrons would be gnats buzzing around the upper bleachers. Everything between them would be empty space. You are mostly nothing. The table is mostly nothing. The wall is mostly nothing. The apparent solidity of matter is not because things are actually solid. It is because of the electromagnetic force, the repulsion between the electron clouds of neighboring atoms, which prevents your hand from passing through the table. Not a physical barrier, an invisible force. Now zoom in further, inside the nucleus. inside a proton. This is where quarks live. A proton contains 3 quarks, held together by what physicists call the strong nuclear force. The quarks are incredibly small as far as we can tell, truly point-like, with no measurable size at all. And they are bound together so fiercely that you cannot separate them. If you try to pull a quark out of a proton, you put so much energy into the attempt that the energy itself creates new quarks, which immediately bind back together. The quark never gets free. Nature refuses to allow a lone quark to exist. This is the world the Standard Model describes. Quarks and electrons and neutrinos, matter particles that make up everything, plus force-carrying particles that mediate the interactions between them. The photon carries the electromagnetic force. Gluons carry the strong force. The W and Z bosons carry the weak force. Each force has its own carrier particles, and the Standard Model describes how all of these particles interact with extraordinary mathematical precision. But here is something about this world that most people never think about. These particles do not exist in a vacuum. They exist in fields. In the Standard Model, the more fundamental concept is not a particle. It is a field that permeates all of space. Every point in the universe, from the densest neutron star to the most remote void between galaxies, is threaded through with these fields. The electron field, the quark fields, the gluon field, the electromagnetic field. Each one is a mathematical entity that has a value at every single point in space and time. A particle, an electron, a photon, a quark is not a little ball floating through empty space. It is a disturbance in a field, a ripple, an excitation. When an electron moves through space, what is actually happening is that the electron field is developing a localized oscillation that propagates from one place to another. The electron is, in a very real sense, made of the field. It is what the field looks like when it has been set vibrating in a particular way. This might seem like an abstract distinction, but it has profound consequences. Because if particles are excitations of fields, then the properties of those particles, their mass, their charge, the forces they experience are determined by the properties of the fields. And the properties of the fields are determined by the mathematics that governs them. And that mathematics, when it comes to the Higgs boson, points to something deeply strange. Let us talk about mass. Mass is so basic to our experience of the world that we rarely question it. Objects have mass. Heavy things are harder to move than light things. Mass creates gravity. Mass is real, obvious, fundamental. But in the Standard Model, at the deepest level, mass is not obvious at all. It is, in fact, a puzzle. Because in the original formulation of the theory, before the Higgs mechanism was introduced, many of the fundamental particles had no mass whatsoever. This is not a mistake in the mathematics. It is a consequence of a symmetry. The Standard Model is built on symmetries. Symmetry, in this context, does not mean visual symmetry, like a butterfly's wings. It means that the equations of physics remain the same even after certain transformations are applied. Rotate the universe in a certain abstract mathematical space, and the laws of physics should be unchanged. The Standard Model is built on a specific set of these symmetries, technically called gauge symmetries, and maintaining those symmetries imposes constraints on what the theory is allowed to contain. One of those constraints, when you work through the mathematics carefully, is that certain particles cannot have mass and still respect the gauge symmetry. Specifically, the W and Z bosons, The carriers of the weak nuclear force are required by the symmetry to be massless, but they are not massless. We have measured their masses. They are enormous. The W boson weighs about as much as 80 protons. The Z boson is slightly heavier. These are among the heaviest particles in the Standard Model, so we have a problem. The symmetry says certain particles must be massless. The experiments say they are not. Something is wrong. The resolution to this problem was worked out in the early 1960s, independently by several physicists. Peter Higgs was among them, along with Francois Englert, Robert Brout, Gerald Guralnick, Carl Hagen, and Tom Kibble. The mechanism they discovered is now called the Higgs mechanism, and it is one of the most elegant ideas in the history of physics. The key insight is this: the symmetry of the theory does not have to be manifested in the state of the universe. The underlying equations can have a symmetry, but the actual physical vacuum, the ground state of the universe, the state of lowest energy, can break that symmetry. This is called spontaneous symmetry breaking. Here is an analogy. Imagine a perfectly symmetric magnet above its Curie temperature, the temperature above which it loses its magnetism. At high temperatures, the magnet has no preferred direction. Every direction is equally likely for the atomic spins to point. The system is symmetric. Now cool the magnet below the Curie temperature. Suddenly, the atomic spins align. They pick a direction, let us say north. The magnet is now magnetized. The symmetry has been broken. Not because the laws of physics changed, but because the lowest energy state of the system is one where a particular direction has been chosen. The Higgs mechanism works on a similar principle, but more profound. There is a new field, the Higgs field, that permeates all of space. At very high energies, like those present in the early universe fractions of a second after the Big Bang, the Higgs field sits at zero. It has a symmetric, featureless ground state. But as the universe cooled, the Higgs field underwent a phase transition, similar to water freezing into ice. It settled into a new ground state with a non-zero value. The Higgs field, everywhere in the universe, now has a value that is not zero. This non-zero value of the Higgs field is what gives particles mass. When the W and Z bosons move through space, they interact with the Higgs field. They cannot simply glide through it. The Higgs field resists their passage. This resistance is what we measure as mass. The stronger a particle interacts with the Higgs field, the more resistance it experiences and the heavier it is. The W and Z bosons interact strongly with the Higgs field, so they are heavy. Photons do not interact with the Higgs field at all, so they are massless. Electrons interact somewhat weakly, so they are light. The Higgs field is the source of mass for everything in the Standard Model. This is a beautiful idea, and it works. It resolves the symmetry problem. It explains why the W and Z bosons are heavy. It explains the masses of quarks and electrons. Every experimental test of the mechanism has confirmed it, but it raises a question, a very sharp question. If there is a Higgs field permeating all of space, then that field should have ripples, disturbances that propagate through the field. And in quantum field theory, those disturbances correspond to a particle, the Higgs boson. This is the particle that Peter Higgs predicted in 1964, the quantum of the Higgs field. The ripple in the ocean of the mechanism that gives everything else its mass. And the mass of that ripple, the mass of the Higgs boson itself, is the problem we have been building toward. Because the Higgs boson's mass is not determined by the same mechanism that determines the masses of other particles. The Higgs field gives mass to quarks and electrons and W bosons. But what gives mass to the Higgs boson itself? The answer in the standard model is the shape of the Higgs field's potential energy, the mathematical function that describes how the Higgs field's energy varies as a function of its value. The Higgs boson's mass is determined by how sharply that potential energy curves near its minimum, and that is where the numbers go catastrophically wrong. Let us talk about what quantum field theory actually predicts for the mass of the Higgs boson. In quantum field theory, the mathematical framework that underlies the standard model, the vacuum of space is not empty. This is not a philosophical statement or a poetic metaphor. It is a precise mathematical fact with measurable consequences. The quantum vacuum is a seething, churning sea of virtual particles that constantly flash in and out of existence, appearing from nowhere and vanishing again in intervals so brief that they cannot be directly observed. These virtual particles are real in the sense that they have measurable effects. They affect the behavior of electrons in magnetic fields. They cause tiny shifts in the energy levels of hydrogen atoms. They produce forces between conductors separated by a vacuum. Every one of these effects has been measured, and every measurement confirms that the quantum vacuum is not empty. It is alive with activity. Now here is where the Higgs boson's mass becomes a problem. The Higgs boson, like every other particle in the standard model, interacts with these virtual particles. Virtual particles pop into existence all around it, interact with the Higgs field, and then disappear. Each of these interactions gives a tiny contribution to the Higgs boson's effective mass. You calculate the bare mass of the Higgs, the mass it would have with no quantum corrections, and then you add up all the contributions from all the virtual particle interactions, and you get the physical mass that you would actually measure in an experiment. This process is called renormalization, and it is a standard part of how quantum field theory works. Every particle's physical mass includes these quantum corrections. For most particles, the corrections are modest. They shift the mass by a calculable amount that physicists can account for, but the Higgs boson is different. Spectacularly, catastrophically different. The Higgs boson's mass receives quantum corrections from every single massive particle in the standard model. Every quark, every heavy lepton, every W and Z boson, all of them contribute virtual corrections to the Higgs boson's mass. And unlike the corrections for other particles, these corrections for the Higgs are not modest. They are enormous. The reason involves the mathematics of how the corrections scale with energy. For most particles, the quantum corrections grow only logarithmically with the energy scale you are considering. Logarithmically means slowly. Even if you extend your theory up to very high energies, the corrections only grow as the logarithm of those energies, which is a gentle, manageable growth. But for the Higgs boson, the corrections grow as the square of the energy. This is called quadratic sensitivity, and it means that if there are any new physics effects at high energies, any new particles, any new interactions, any new structure, those effects will contribute quadratically to the Higgs mass. The Higgs mass is exquisitely sensitive to what happens at high energies in a way that no other particle's mass is. Now consider what we know about physics at high energies. We know that gravity exists. We know that at some energy scale, the Planck scale gravity becomes as strong as the other forces, and quantum gravitational effects must become important. The Planck scale is at an energy of roughly 10 to the power of 19 billion electron volts. The Higgs boson has a measured mass of about 125 billion electron volts. The ratio between the Planck scale and the Higgs mass is roughly 10 million billion. Written out as a number, that is a 1 followed by 16 zeros. Now calculate the quantum corrections to the Higgs boson mass from virtual particles at the Planck scale. Because of the quadratic sensitivity, those corrections are of order the Planck scale squared. They are enormous, roughly 10 to the power of 38 billion electron volts squared. They should push the Higgs mass up to the Planck scale. They should make it enormously, grotesquely heavy. And yet the physical Higgs boson mass is 125 billion electron volts. To get from an enormous correction of order, the Planck scale squared to a physical mass of 125 billion electron volts, you need a cancellation. The bare mass of the Higgs, the mass before quantum corrections, and the quantum corrections themselves must cancel each other with extraordinary precision. They must cancel to roughly 1 part in 10 to the power of 34. Think about what that means. You have 2 enormous numbers. Each one is of order the Planck scale squared, which is unimaginably large, and they must cancel each other, leaving behind a tiny residual that is the observed Higgs mass. The cancellation must be accurate to 34 decimal places. That is the hierarchy problem. Let me make this concrete with an analogy. Imagine you are calculating your bank balance at the end of the year. You have received income and made expenditures throughout the year. Now imagine that your income was $10 trillion, a number with 13 digits. Your expenditures were also approximately $10 trillion. The difference, your actual balance, is $1. So the income and expenditures must cancel to 13 digits of precision. That $1 balance is the result of 2 $10 trillion numbers agreeing to 13 decimal places. Now imagine those numbers had 34 digits. The income would be a 1 followed by 34 zeros of dollars. The expenditures would be essentially the same enormous number. And the result, the Higgs mass, is a small number that requires those 2 incomprehensibly large quantities to cancel to 34 decimal places of precision. Is that possible? In a narrow mathematical sense, yes. There is nothing in the laws of physics that prevents such a cancellation. The bare mass and the quantum corrections are both free parameters, and they are free to take whatever values produce the observed physical mass. But physicists find this deeply unsatisfying, and here is why. When something in physics appears to be fine-tuned, when it looks like you have had to adjust parameters with extreme precision to reproduce what you observe, it usually means one of 2 things. Either you are missing something, and the fine-tuning is an illusion created by an incomplete understanding of the underlying physics, or the universe, for reasons you do not understand, just happens to be arranged that way. The first possibility is hopeful. It suggests there is a deeper explanation that, once found, will make the fine-tuning disappear. The mechanism will reveal itself, and you will see that the parameters were not arbitrary at all. They were dictated by some deeper principle you had not yet discovered. The second possibility is deeply uncomfortable for most physicists. It is essentially giving up. It is saying that the universe chose its parameters at random, and we happen to get lucky. That is a valid philosophical position. The universe does not owe us an explanation, but it is not a satisfying scientific answer, and it does not have a good track record in physics. Every time in history that physicists have encountered what appeared to be fine-tuning, deeper physics has eventually resolved it. when atomic sizes seemed puzzlingly stable and precise, quantum mechanics explained why. When the cosmological constant in Einstein's original equations seemed to require fine-tuning to match observations, it forced the development of new ideas about cosmic expansion. The expectation, grounded in a century of scientific experience, is that apparent fine-tuning is a signal pointing toward undiscovered physics. The hierarchy problem is the fine-tuning problem for the Higgs boson mass, and physicists have been trying to solve it for nearly 40 years. The solutions that have been proposed are among the most beautiful and ambitious ideas in modern theoretical physics. They involve supersymmetry, extra dimensions, composite particles, and entirely new organizing principles for the laws of nature. Each one attacks the hierarchy problem from a different angle. Each one predicts new particles, new forces, new phenomena, and so far none of them have been confirmed by experiment. That is the situation we are in, a profound theoretical problem, multiple candidate solutions, and an experiment, the Large Hadron Collider, that has searched for these solutions and found nothing yet. This is not a failure of science. It is science working exactly as it should, confronting the hardest problems at the frontier of knowledge and refusing to look away. But it is unsettling, and it raises questions about our understanding of the universe that nobody knows how to answer. Let us explore those solutions. Let us see what they predict and why physicists found them compelling. And let us be honest about why the LHC's silence has shaken confidence in ideas that seemed, for decades, nearly inevitable. Before we proceed to the proposed solutions, it is worth pausing to understand something that makes the hierarchy problem uniquely severe for the Higgs boson. Because the immediate question a thoughtful person might ask is, if quantum corrections push particles toward higher masses, why are other particles not also dragged up to the Planck scale? Why is it only the Higgs that has this problem? The answer reveals something deep about the structure of the Standard Model and why the Higgs occupies such a special and precarious position. Consider the electron. The electron has a very small mass, about 0.511 million electron volts. Compared to the Planck scale, the electron mass is tiny. So why does the hierarchy problem not apply to the electron the same way it applies to the Higgs? The answer is chirality. The electron comes in two varieties, left-handed and right-handed. In the Standard Model without the Higgs mechanism, these two versions of the electron are separate, independent particles with their own distinct identities. They interact with different forces. The left-handed electron interacts with the W boson. The right-handed electron does not. They are genuinely different objects. For the electron to have a mass, the left-handed and right-handed versions must mix together. A mass term in the quantum field theory equations couples left-handed fields to right-handed fields. And this means that in a theory with a chiral symmetry, one that treats left-handed and right-handed particles separately, an electron mass term is forbidden by the symmetry. The mass of the electron breaks a symmetry. And when a particle's mass breaks a symmetry, something powerful happens in the quantum world. The quantum corrections to that particle's mass are proportional to the mass itself. If the electron mass is small, the corrections are small. The electron mass is what physicists call technically natural. It is protected against large corrections by the chiral symmetry that its mass breaks. Setting the electron mass to a small value is not fine-tuning. It is placing a symmetry-breaking term at a small value, which is stable against quantum corrections. This is the concept of technical naturalness, introduced by Gerard 't Hooft in 1979. 't Hooft's insight was that a parameter in a theory is technically natural if, in the limit where that parameter goes to zero, the theory acquires an additional symmetry. When the electron mass goes to zero, chiral symmetry is restored. So a small electron mass is technically natural. It does not require fine-tuning because the symmetry explanation makes it stable. The same logic applies to the quarks, to the muon, to the tau lepton. All of these particles have small masses relative to the Planck scale, but all of them are technically natural because their masses break chiral symmetries. The W and Z bosons get their masses from the Higgs mechanism, specifically from the non-zero vacuum expectation value of the Higgs field. Their masses are controlled by the Higgs vacuum expectation value, which is itself controlled by the Higgs mass. So in a sense, the W and Z masses have the hierarchy problem too, but it is inherited from the Higgs. The gauge bosons, photons, and gluons are massless, and they are protected by gauge symmetry. Setting their masses to zero is infinitely natural, because gauge symmetry absolutely forbids them from acquiring mass. So we have an inventory. Fermion masses are protected by chiral symmetry. Gauge boson masses are protected by gauge symmetry. The Higgs vacuum expectation value is protected by nothing. The Higgs boson is a scalar particle. It has spin zero, and scalar particles are special in a terrible way. In quantum field theory, scalar masses have no symmetry protection. There is no chiral symmetry for scalars, because scalars do not come in chirality eigenstates. There is no gauge symmetry protecting scalar masses from quantum corrections, because scalars are not gauge fields. Scalar masses are exposed to the full force of quantum corrections from every energy scale in the theory. This is why the Higgs is special. It is the only fundamental scalar in the Standard Model, and scalar particles are uniquely vulnerable to the hierarchy problem. To 't Hooft's criterion of technical naturalness, the Higgs mass fails dramatically. Setting the Higgs mass to zero does not restore any new symmetry of the Standard Model. There is no additional symmetry that would be protected. The limit of zero Higgs mass is not special in any symmetry sense. Therefore, the Higgs mass is not technically natural. It is not protected against large quantum corrections. Every virtual particle of every species contributes to pushing it up toward the highest energy scales present in the theory. And the only way to keep it at 125 billion electron volts is to fine-tune the bare mass against the corrections to extraordinary precision. This is why the hierarchy problem is considered one of the deepest problems in theoretical physics, and not merely an aesthetic complaint. It is a precise, quantifiable statement about the absence of technical naturalness in the Higgs sector. It asks, in the absence of any symmetry protection, why is the Higgs mass so small? And it has no answer within the Standard Model. Understanding this also clarifies what a good solution would look like. A good solution to the hierarchy problem would be a mechanism that gives the Higgs mass technical naturalness, that identifies a symmetry which, in the limit where the Higgs mass goes to zero, is restored. Supersymmetry does exactly this. In a supersymmetric theory, scalar masses are related to fermion masses by the supersymmetry itself, and fermion masses are technically natural. Supersymmetry elevates scalar masses to the same protected status as fermion masses. This is the real reason supersymmetry was so compelling. It did not just provide a mechanism for canceling corrections. It provided a symmetry, and symmetry-based explanations have historically been among the deepest and most reliable in all of physics. For decades, supersymmetry was the favored solution to the hierarchy problem. It is not hard to understand why. Supersymmetry is, in a certain precise mathematical sense, the most beautiful extension of the standard model that anyone has ever written down. It solves multiple problems simultaneously, connects ideas that seem unrelated, and points toward a deeper unification of the forces of nature. If physics had an aesthetic criterion, and in some ways it does, because beauty and elegance have historically been reliable guides to truth in fundamental physics, then supersymmetry would score extraordinarily well. The basic idea of supersymmetry is this. In the standard model, particles come in two varieties. Fermions are the matter particles, quarks, electrons, neutrinos. They obey a quantum mechanical rule called the Pauli exclusion principle, which prevents two identical fermions from occupying the same quantum state. Bosons are the force-carrying particles, photons, gluons, W and Z bosons, the Higgs. They do not obey the exclusion principle. You can pile as many identical bosons into the same state as you want. Supersymmetry proposes a new symmetry between these two types of particles. For every fermion in the standard model, supersymmetry predicts a corresponding boson, a superpartner with identical properties, except that it is a boson instead of a fermion. And for every boson, supersymmetry predicts a corresponding fermion. The electron, a fermion, would have a partner called the selectron, a boson. The photon, a boson, would have a partner called the photino, a fermion. The quarks would have partners called squarks. The gluons would have partners called gluinos. The Higgs boson would have a partner called the Higgsino. This doubling of the particle content might seem like unnecessary complexity. Why add all these new particles that no one has ever observed? The answer is that supersymmetry does something remarkable for the hierarchy problem. Remember the problem. Virtual particles from all massive species in the universe contribute quantum corrections to the Higgs boson mass. Fermions contribute corrections of one sign. Bosons contribute corrections of the opposite sign. In an ordinary theory, these contributions do not cancel. You add up the contributions from all the known particles and get a correction that is enormous, pushing the Higgs mass toward the Planck scale. But in a supersymmetric theory, every fermion has a boson partner with exactly the same mass. This means that for every fermionic correction to the Higgs mass, there is an equal and opposite bosonic correction. They cancel. Exactly. Not approximately, not to 34 decimal places of fine-tuning, but exactly by mathematical necessity. The quadratic corrections that drive the Higgs mass toward the Planck scale simply vanish, as if by magic. The Higgs mass is stable against quantum corrections. This is the supersymmetric solution to the hierarchy problem. It is called a natural solution because the cancellation is not the result of fine-tuning, it is the result of symmetry. When a symmetry is responsible for a cancellation, physicists call that natural. When there is no symmetry and you just have to hope the numbers work out, that is unnatural. Supersymmetry makes the Higgs mass natural, and that is not all it does. In many supersymmetric theories, the lightest supersymmetric particle, sometimes called the LSB, is stable. It cannot decay into anything lighter, and in the most studied versions of the theory, this LSB is electrically neutral and interacts with ordinary matter only through the weak force and gravity. It is, in other words, a particle that is heavy, stable, electrically neutral, and weakly interacting. It barely interacts with ordinary matter and cannot be seen by any telescope. It is, in other words, an excellent candidate for dark matter. Supersymmetry, introduced to solve the hierarchy problem, simultaneously provides a candidate for dark matter. Two enormous mysteries of physics addressed by the same theory. This kind of convergence, where one new idea solves multiple unrelated problems, is exactly what physicists look for in a true advance. But there is more. The three forces of the Standard Model, electromagnetic, strong, and weak, have different strengths at the energies we can currently probe. The electromagnetic force is weaker than the strong force. The weak force is different again. But when you extrapolate these force strengths to higher and higher energies using the Standard Model equations, you find that they converge toward each other, but not quite to a single point. They nearly unify, but not exactly. In a supersymmetric theory, the additional particles change the way the force strengths evolve with energy. And when you include the supersymmetric partners, the three forces converge to a single strength at a common energy scale, roughly 10 to the power of 16 billion electron volts. This energy scale is called the grand unification scale, and the fact that supersymmetry enables exact unification is deeply suggestive. It hints that at high enough energies, all three forces are actually manifestations of a single unified force, three problems solved at once. The hierarchy problem, dark matter, grand unification, all addressed by a single extension of the Standard Model. This is why supersymmetry became the dominant paradigm in theoretical particle physics for the latter decades of the 20th century and into the 21st. It was not wishful thinking. It was responding to genuinely compelling mathematical structure. And there was one more reason for optimism. The supersymmetric partners could not be infinitely heavy. If they were too heavy, they would not solve the hierarchy problem, the cancellations would not be complete enough, and you would be back to fine-tuning. Estimates varied, but the broad consensus was that if supersymmetry solved the hierarchy problem naturally, the superpartner particles should have masses below roughly a few thousand billion electron volts, a few TeV in the units physicists use. The Large Hadron Collider operates at energies up to 13 TeV. If supersymmetric particles existed in the mass range needed to solve the hierarchy problem naturally, the LHC should have found them. It has not. After more than a decade of data collection, after billions of collisions analyzed, after the most sophisticated search algorithms ever developed have been applied to the data, no superpartner has been detected. No selectron, no squark, no gluino, no neutralino. Not one particle from the predicted supersymmetric spectrum has appeared. The LHC has pushed the limits on superpartner masses to energies of several TeV, in some cases approaching 2 or 3 TeV for the most strongly interacting particles. This does not definitively rule out supersymmetry. The superpartners could still exist, just at masses higher than current sensitivity. But it puts them in a mass range where, if they exist, they no longer naturally solve the hierarchy problem. To get the right Higgs mass with superpartners that heavy, you need a degree of fine-tuning. Not as much fine-tuning as you need without supersymmetry, but fine-tuning nonetheless. This is the uncomfortable situation supersymmetry finds itself in. Its original motivation, naturalness, is becoming strained. The particle spectrum needed for a natural solution to the hierarchy problem is increasingly excluded by data. Versions that survive the LHC constraints are versions where the solution is somewhat unnatural. Some physicists have responded by adjusting their definitions of naturalness, arguing that a modest degree of fine-tuning is acceptable. Others have proposed more complex variants of supersymmetry that hide the superpartners in ways that make them harder to detect. Still others have begun to question whether naturalness is the right criterion to begin with. Perhaps nature simply chose a fine-tuned Higgs mass, and we need to accept that. None of these responses are fully satisfying. And the failure to find supersymmetry at the LHC has produced a genuine crisis of confidence in the theoretical physics community, a reckoning with the question of whether the intuitions that guided decades of work were actually pointing in the right direction. But supersymmetry is not the only idea. It is the most famous, but it is far from alone. If supersymmetry is the most elegant proposed solution to the hierarchy problem, extra dimensions might be the most audacious. The idea that space might have more than 3 dimensions has a long history in physics. In the 1920s, mathematicians Theodore Kaluza and Oskar Klein proposed that there might be a 4th spatial dimension, curled up at such a small scale that it is invisible to everyday observation. They were motivated by the tantalizing mathematical observation that Einstein's equations of general relativity in 5 dimensions, when reduced to 4, automatically produce both Einstein's gravity in 4 dimensions and Maxwell's equations of electromagnetism. 2 seemingly unrelated theories emerge naturally from a single unified framework in higher dimensions. The Kaluza-Klein idea was beautiful, but lacked experimental motivation at the time. For decades, extra dimensions remained a mathematical curiosity rather than a serious physical proposal. That changed in the late 1990s, when a series of papers proposed that extra dimensions might actually solve the hierarchy problem. The key insight came from physicists Nima Arkani-Hamed, Savas Dimopoulos, and Gia Diwali in 1998, and separately from Lisa Randall and Raman Sundram the following year. These proposals are distinct in their details, but they share a common theme. Extra dimensions can explain why gravity is so much weaker than the other forces. Remember the hierarchy problem in its other form. The Planck scale, the energy at which gravity becomes as strong as the other forces, is 16 orders of magnitude higher than the electroweak scale, the scale of the Higgs mass. This enormous hierarchy of scales requires the Higgs mass to be fine-tuned to extraordinary precision. But what if the Planck scale is not actually 16 orders of magnitude above the electroweak scale? What if gravity only seems weak because it is spreading into extra dimensions? Here is the idea. Imagine you have a room with a powerful speaker in the corner. The sound fills the entire room. If someone walks in from outside, they hear the music at full volume. Now imagine that the room has a trapdoor in the floor, leading to an enormous underground space. Some of the sound leaks into that underground space. A listener in the room hears less music. The apparent strength of the sound source has been diluted. Gravity might work similarly. The standard model forces electromagnetism. The strong force, the weak force are confined to our 4-dimensional spacetime. Their force-carrying particles cannot escape into extra dimensions, but gravity is different. Gravity in general relativity is the curvature of spacetime itself. If there are extra dimensions of spacetime, gravity spreads into them. It is diluted by the extra volume. This would explain why gravity appears so much weaker than the other forces. It is not intrinsically weaker. It is just that most of its strength has leaked into dimensions we cannot directly observe. The fundamental Planck scale, the energy at which gravity's true strength becomes apparent, might actually be much closer to the electroweak scale. The apparent weakness of gravity is an artifact of extra dimensions. If this is correct, then the hierarchy problem is not a problem about fine-tuning. It is a problem about our mistaken assumption that there are only 3 spatial dimensions. Include the extra dimensions and the mystery dissolves. The Randall-Sundrum model takes a different approach. Rather than large flat extra dimensions, it proposes a single extra dimension shaped by a specific spacetime geometry, a warped geometry in which the physical scale of distances varies exponentially along the extra dimension. In this setup, gravity is localized near one end of the extra dimension, one brane in the technical jargon, and we live on a second brane at the other end. The exponential warping means that energies on our brane are exponentially smaller than energies on the other brane. What appeared to be a vast hierarchy between the Planck scale and the electroweak scale becomes, in the Randall-Sundrum picture, simply a reflection of our position in the extra dimension. The hierarchy is generated geometrically, not by fine-tuning of parameters. These extra-dimension proposals make concrete, testable predictions. In the Arcani-Haim-Dimopoulos-Diwali model, gravitons, the hypothetical particles that carry gravity, can escape into the extra dimensions. This would show up as apparent violations of energy conservation in particle collider experiments, where collisions seem to produce less energy than they started with, because some energy has been carried away by gravitons escaping into the extra dimensions. This signal is called missing energy, and it is something the LHC has searched for extensively. In the Randall-Sundrum model, the geometry of the extra dimension predicts a series of new particles called Kaluza-Klein gravitons. These would be excitations of the graviton that carry the quantum number associated with motion in the extra dimension. They would appear as resonances, spikes in the rate of particle production at specific energies in LHC collision data. These two have been searched for. Neither signal has been found. The LHC has placed stringent limits on the existence of the extra dimensions predicted by these models. In the Arcani-Haim-Dimopoulos-Diwali scenario, the extra dimensions would need to be smaller than about 1/10 of a millimeter, much smaller than the original proposals, and too small to solve the hierarchy problem in the original way. In the Randall-Sundrum scenario, the Kaluza-Klein gravitons would need to be heavier than several TeV, again pushing the new physics to scales where it no longer naturally solves the problem. The pattern is the same as with supersymmetry. The models survive but are strained. The original motivation, natural solutions to the hierarchy problem, is being eroded as the null results from the LHC push the new particles to higher and higher masses, where the solutions require increasing degrees of fine-tuning to reproduce the observed Higgs mass. This is not to say that extra dimensions are ruled out. They might exist. The universe might genuinely have more spatial dimensions than 3, but the specific versions proposed as solutions to the hierarchy problem are increasingly disfavored by the data. There is something important to notice here. The hierarchy problem was supposed to tell us where new physics would appear. It pointed to a specific energy scale, the TeV scale, and predicted that new particles should show up there. The LHC was built in significant part to discover those particles, and the particles have not appeared. This silence is not just a failure of particular models. It is a failure of a general expectation about how the hierarchy problem should be solved. The expectation was that nature is natural, that the fine-tuning of the Higgs mass would be explained by new physics that appears just above the electroweak scale. The LHC has tested that expectation and so far found it wanting. This is what physicists are grappling with now. Not just the absence of any particular predicted particle, but the possible failure of naturalness as a guiding principle. The possibility that the universe is, in fact, fine-tuned and that we do not understand why. That possibility leads to some of the most radical ideas in modern physics. There is another class of solutions to the hierarchy problem, distinct from supersymmetry and extra dimensions, that takes a completely different approach to the question. What if the Higgs boson is not a fundamental particle at all? In the standard model, the Higgs is treated as elementary, a true point particle with no internal structure, like the electron or the photon. But there is historical precedent for apparently elementary particles turning out to have substructure. The proton seemed fundamental until the 1960s, when experiments at the Stanford Linear Accelerator Center revealed that it contained quarks. The neutron, the pion, the kaon, all of these were once thought to be fundamental, and all of them turned out to be composite states of quarks and gluons. If the Higgs boson is composite, if it is made of smaller constituents bound together by some new force, then the hierarchy problem changes its character entirely. The reason the Higgs mass receives enormous quantum corrections is that the Higgs is a fundamental scalar particle. Scalar means it has no intrinsic spin. All other fundamental particles in the standard model either have spin-half fermions or spin-1 gauge bosons, and for those particles, quantum corrections to the mass are protected by symmetries: spin symmetry for fermions, gauge symmetry for bosons. But the Higgs has spin 0, and scalar particles have no such protection. Their masses are vulnerable to quantum corrections from the highest energy scales in the theory. A composite particle does not have this problem. The mass of a composite particle is determined primarily by the binding energy of whatever new force holds its constituents together, not by quantum corrections that reach up to the Planck scale. The Higgs mass in a composite model is naturally of order the energy scale of the new binding force, and if that binding force operates at the TV scale, the Higgs mass comes out naturally at the right value. This idea was first developed in the 1970s under the name Technicolor. The Technicolor proposal postulated a new strong force analogous to the strong nuclear force, but operating at a higher energy scale that bound together new fundamental particles called technifermions. The Higgs boson would be a composite state of these technifermions, and the electroweak symmetry breaking would be driven by the condensation of technifermion-antitechnifermion pairs, analogous to the way that quark-antiquark condensation drives chiral symmetry breaking in ordinary QCD. Technicolor was a beautiful idea. It was motivated by well-understood physics, the analogy with QCD, and it naturally generated symmetry breaking at the electroweak scale without any fine-tuning. But it ran into severe problems. The main problem was that Technicolor, in its simplest form, predicted that the fermions, quarks, and electrons would be massless. Generating fermion masses required extending the theory in ways that led to conflicts with precision electroweak measurements. The extended versions of Technicolor, designed to generate fermion masses, predicted deviations from standard model predictions that were not observed in experiments. By the late 1990s, Technicolor was largely abandoned as a direct competitor to the standard model, but the underlying idea, a composite Higgs, was revived in a more sophisticated form in the early 2000s. The modern version, called the Composite Higgs model, uses insights from extra-dimensional theories to construct theories where the Higgs is a composite particle arising from some new strong dynamics, but where the dangerous corrections that plagued old Technicolor models are suppressed by additional symmetry structures. In many composite Higgs models, the Higgs boson is what physicists call a pseudo-Nambu-Goldstone boson. When a continuous symmetry is spontaneously broken, the theory predicts the existence of massless particles called Nambu-Goldstone bosons. If the symmetry is only approximate, if it is slightly broken by some explicit terms, then the would-be Nambu-Goldstone bosons acquire small masses. They are pseudo-Nambu-Goldstone bosons. The Higgs boson in this picture is one of these pseudo-Nambu-Goldstone bosons. Its mass is small not because of a fine-tuning, but because it is protected by the approximate symmetry. The smallness of the Higgs mass is related to the degree to which that underlying symmetry is explicitly broken, and that breaking can be arranged to be small without fine-tuning. This is a natural solution to the hierarchy problem. The Higgs mass is stabilized not by supersymmetric cancellations, not by extra-dimensional geometry, but by the Higgs being a composite pseudo-Nambu-Goldstone boson of some new strong dynamics at the TV scale. Composite Higgs models make predictions. They predict that the Higgs boson should have slightly different properties from the standard model Higgs. Its couplings to other particles should be modified by small corrections proportional to the ratio of the Higgs mass to the compositeness scale. They predict new resonances, heavier composite partners of the top quark, and the electroweak gauge bosons in the TV range. These partners are called top partners, and their presence is crucial for the naturalness of the Higgs mass in composite models. The LHC has searched for top partners. It has searched for modified Higgs couplings. It has looked for the signatures of new strong dynamics. So far, no top partners have been found. The Higgs couplings have been measured with increasing precision, and they agree with standard model predictions to within about 10%, leaving some room for compositeness, but squeezing the allowed parameter space steadily smaller. Composite Higgs models remain viable, but they too are under pressure. The natural versions of these models predicted top partners in the mass range of roughly 500 to 1,000 billion electron volts. The LHC has pushed the limits on top partners to above 1 TeV for the most accessible signatures, again pushing the allowed parameter space into regions where some residual fine-tuning creeps back in. The hierarchy problem is not solved by composite Higgs models at this moment. It is deferred, shifted to a somewhat higher scale, but not eliminated. And this brings us to the most uncomfortable possibility of all. What if the Higgs mass is simply fine-tuned? What if the universe is not natural and there is no new physics around the TV scale? What if the mechanism that set the Higgs mass is not something discoverable at particle accelerators at all? This possibility has a name. It is called the multiverse argument, or more technically, the Anthropic principle applied to the Higgs mass, and it is deeply controversial. There is a version of reality in which the hierarchy problem is not a problem at all. In this version, the universe we inhabit is one of an enormous, perhaps infinite number of universes, each with its own values of the fundamental constants. Different universes have different Higgs masses, different strengths of the forces, different numbers of particle generations. Most of these universes are sterile. In most of them, the Higgs mass is enormous, and atomic nuclei do not form, and stars do not shine, and complexity never arises. But some universes, a tiny fraction, happen to have a Higgs mass in the right range for matter to be stable, for chemistry to occur, for planets to form and life to develop. We find ourselves in one of those universes not because the parameters were chosen for us by some deeper principle, but simply because in universes where the parameters are wrong, there is no one to ask why they are what they are. This is the anthropic argument, and applied to the Higgs mass, it says that the fine-tuning is not pointing toward undiscovered physics. It is pointing toward a landscape of universes, in which observers can only find themselves in the rare universes where the parameters are compatible with their existence. The anthropic principle has a long and contentious history in physics and philosophy. It is technically unfalsifiable. There is no experiment you can perform to test the existence of other universes with different physical constants. For this reason, many physicists regard it with deep suspicion. Science, in their view, must be grounded in empirically testable predictions. A theory that explains everything by appeal to an unobservable multiverse is not a scientific theory in any meaningful sense. It is metaphysics dressed as physics. But defenders of the anthropic approach point out that it has made at least one genuine prediction. In 1987, physicist Steven Weinberg used anthropic reasoning to predict the value of the cosmological constant, the energy density of the vacuum that drives the accelerating expansion of the universe. The cosmological constant has its own fine-tuning problem. It is observed to be enormously smaller than quantum field theory naively predicts. Weinberg argued that in a landscape of universes, the cosmological constant cannot be too large and positive, or it would drive the universe to expand so fast that galaxies would never form and observers would never exist. The anthropic constraint limits the cosmological constant to values small enough to allow structure formation. 11 years later, the cosmological constant was measured for the first time through observations of distant supernovae. The measured value was small, comparable to the anthropic bound Weinberg had estimated. This was widely regarded as a success for anthropic reasoning, not a definitive confirmation, but a suggestive agreement. Could the same logic apply to the Higgs mass? There is a version of the anthropic argument for the Higgs mass. The Higgs mass determines the masses of the W and Z bosons, which in turn affect the rate of weak interactions. The weak interactions govern, among other things, the rate at which protons decay into neutrons and vice versa in the early universe, which affects the abundance of hydrogen and helium after the Big Bang, which affects the properties of stars. A Higgs mass much larger than the observed value would change the nuclear physics of stars in ways that might make carbon production much less efficient. Carbon is, of course, the basis of chemistry as we know it. So one can construct an anthropic argument. The Higgs mass cannot be too different from its observed value, because if it were, the carbon-based chemistry needed for observers would not exist. We find a Higgs mass in the right range because in universes where it is wrong, no one is around to notice. This argument is not watertight. The connection between the Higgs mass and the possibility of carbon-based life is indirect and model-dependent. Small changes in the Higgs mass might be compensated by small changes in other parameters, allowing life to persist. The anthropic window for the Higgs mass, if one exists, is not sharply defined, but the logic is coherent. And as supersymmetry and extra dimensions have failed to materialize at the LHC, some physicists have found themselves reluctantly entertaining the possibility that anthropic selection might be at work. This is a profound shift in the culture of particle physics. For generations, the field has been guided by the principle of naturalness, the belief that fundamental parameters of physics have the values they do because of some underlying symmetry or dynamical mechanism, not because we happen to be here. Naturalness has been extraordinarily productive. It motivated the development of supersymmetry. It predicted the top quark's mass before it was measured. It drove much of the theoretical work that led to the Standard Model. If naturalness fails, if the Higgs mass is simply fine-tuned, with no deeper explanation, it would represent the most significant failure of a guiding principle in the history of modern physics. Some physicists argue that we should not abandon naturalness yet. The LHC has only explored energies up to 13 TeV. New physics could exist at higher energies, outside its reach. The hierarchy problem would still be solved by some mechanism at a scale we have not yet probed. The absence of new physics at the TeV scale is a constraint on models, but not a refutation of the principle. Others argue that the writing is on the wall. The simplest natural models, the ones that physicists found most compelling, predicted particles at the energies the LHC has already explored. Their absence is not neutral evidence. It is evidence against. The debate is ongoing. It is one of the most fundamental disagreements in theoretical physics today, and its resolution will shape the direction of the field for decades. But there is another crack in the Standard Model, one more empirical and less philosophical, that deserves attention here. Because whatever is causing the hierarchy problem, there is additional evidence that the Standard Model is missing something. Evidence that comes not from our discomfort with fine-tuning, but from things the universe has actually shown us. The hierarchy problem is a theoretical problem. It arises from the mathematics of quantum field theory and what it predicts the Higgs mass should be. No experiment has directly confronted us with the hierarchy problem in the way that a measurement that contradicts a prediction confronts us with a discrepancy. It is, in a sense, a problem of expectations rather than observations. But there are other, more empirical reasons to believe the Standard Model is incomplete. There are experiments that have produced results that do not quite match what the theory predicts. Not dramatic failures, not wildly wrong answers, but persistent, stubborn deviations, whispers from the data suggesting that something is there that the Standard Model does not account for. The most compelling of these involves the muon. The muon is the electron's heavier sibling. Everything about it is identical to the electron, same electric charge, same spin, same interactions with the forces of nature, except that it is about 207 times heavier. Nobody knows why it exists. When the muon was first discovered in 1936, coming from cosmic rays hitting the upper atmosphere, the physicist Isidore Isaac Rabi famously responded with what became one of the most quoted lines in the history of particle physics. Who ordered that? It seemed like an unnecessary redundancy, a heavier copy of the electron that played no obvious role in the architecture of matter. But the muon turned out to be an extraordinarily useful probe of the Standard Model. Because the muon's properties can be predicted and measured with extraordinary precision, here is what you need to know. Every charged particle that spins behaves like a tiny magnet. The strength of this magnetism can be characterized by a dimensionless number physicists call G. For a simple spinning charged particle described by the most basic quantum mechanics, G should equal exactly 2. But the real quantum world is more complicated. The vacuum around the muon is not empty. It is filled with virtual particles popping in and out of existence, briefly interacting with the muon and then disappearing. Each of these fleeting interactions nudges the muon's magnetic moment slightly away from the simple value of 2. The total accumulated effect of all these virtual interactions is called the anomalous magnetic moment. Physicists denote it G-2 because they are measuring how much G deviates from 2. The Standard Model allows you to calculate G-2 for the muon by adding up contributions from every type of virtual particle. Photons, quarks, gluons, W and Z bosons, Higgs bosons, neutrinos, everything the Standard Model contains. The calculation is staggeringly difficult. It has occupied hundreds of theoretical physicists for decades, but the result is a specific prediction, and the measurement is equally spectacular. At Fermilab outside Chicago, physicists built a 50-foot diameter superconducting ring, the Muon G2 storage ring, to measure the anomalous magnetic moment with extraordinary precision. Muons are injected into this ring, where they circulate at nearly the speed of light, wobbling as they go. The rate of their wobbling depends on G-2. By measuring that wobble with extreme care, physicists can determine the anomalous magnetic moment to incredible precision. The results, reported in 2021 and updated in subsequent runs, show a clear discrepancy. The measured value of G-2 is slightly higher than the Standard Model prediction. Not by a lot. We are talking about a discrepancy in the 9th decimal place. But at the level of precision these experiments achieve, that discrepancy is significant. The combined data shows a tension between theory and experiment that is statistically meaningful, what physicists call roughly a 4 to 5 sigma deviation, depending on which theoretical calculation is used as the benchmark. This cannot be dismissed as experimental error. The apparatus is extraordinarily well characterized. Multiple independent analyses of the data have confirmed the result. The measurement itself is, in many respects, the most precisely controlled physics experiment ever performed. The uncertainty lies on the theoretical side. Calculating G-2 for the muon from first principles requires dealing with contributions from the strong force, specifically virtual quarks and gluons that briefly pop out of the vacuum and influence the muon's magnetism. These contributions, called hadronic vacuum polarization, are notoriously difficult to calculate precisely because the strong force at low energies is intractable using standard perturbative methods. There are two main approaches. One uses experimental data from electron-positron collisions to estimate the hadronic contribution. This approach has been the standard for decades and gives a prediction that disagrees with the Fermilab measurement. The other approach uses lattice QCD, a computational technique where physicists simulate the strong force on supercomputers, by discretizing spacetime into a grid and calculating quark and gluon behavior directly. Some lattice calculations give results closer to the Fermilab measurement, potentially reducing or eliminating the discrepancy. The two approaches currently disagree with each other, and the physics community is working to understand why. But here is what makes this significant. If the discrepancy survives, if the theoretical calculation is eventually confirmed, and the measurement stands, then there is something interacting with the muon that is not in the standard model. Some new particle or force that contributes virtual corrections to the muon's magnetic moment. The standard model, by construction, already includes everything that is known. If the prediction is wrong, it is because there is something unknown that the calculation is missing. Something beyond the standard model. This is the significance of the Muon G-2 anomaly. It is not a crisis, the measurement is precise, but the theoretical situation is complicated. It is not a discovery of new physics, not yet. It is a whisper. An insistent, statistically meaningful whisper that refuses to go away, suggesting that the standard model might be missing something that interacts with the muon. Beyond the muon, there are other anomalies. The flavor anomalies at the LHCb experiment, which studied the decays of particles called B mesons, found patterns inconsistent with the standard model's prediction that the forces should treat electrons and muons identically. Updated analyses have softened some of these discrepancies, but the overall picture, multiple measurements in multiple observables, all showing slight deviations in the same direction, remains intriguing. The W boson mass measured by the CDF2 collaboration at Fermilab was found to be significantly heavier than the standard model predicts, with a discrepancy of about 7 standard deviations. But this result conflicts with measurements from other experiments, including the Atlas detector at the LHC, which found a value consistent with the standard model. The community has not reached a consensus on whether this represents new physics or an undetected systematic error in one of the measurements. And then there are the neutrinos. We have known for over 2 decades that neutrinos have mass. The original standard model predicted that neutrinos would be massless. Experiments studying solar neutrinos and atmospheric neutrinos showed definitively that neutrinos oscillate, they change from one flavor to another as they travel, and oscillation requires mass. This is not an anomaly or a whisper. It is a confirmed definitive departure from the original standard model. Neutrino masses require new physics. They require extending the standard model beyond its original formulation. The extensions that add neutrino masses, whether by introducing right-handed neutrinos, by allowing Majorana mass terms, or by invoking the seesaw mechanism, all go beyond the minimal standard model. Each of these discrepancies, the Muon G-2, the flavor anomalies, the W boson mass, the neutrino masses, points in the same direction, not dramatically. Not with certainty, but together they form a pattern of hints that the standard model is not quite telling the whole story, and the Higgs boson itself might be carrying the most important clue of all. There is another dimension to the Higgs boson story that most people have not heard of, and it is perhaps the most unsettling implication of the measured Higgs mass. It concerns not just the properties of the Higgs boson, but the long-term stability of the universe itself. In the standard model, the Higgs field has a potential energy, a mathematical function that describes how the field's energy varies as a function of its value. The shape of this potential determines the vacuum state of the universe. The universe, like any physical system, seeks the lowest energy state available. The ground state, the vacuum, is the configuration of the Higgs field that minimizes the potential energy. For the standard model to make sense, this minimum must be stable. The Higgs field must be sitting at a true minimum of the potential, a configuration from which small disturbances cannot dislodge it. If the universe is in a true minimum, it can stay there forever. But if the Higgs field is sitting at a local minimum, a configuration that looks like a minimum nearby, but is not actually the lowest energy state globally, then the universe might, through a quantum mechanical process called tunneling, transition to the true lower energy minimum. This would be catastrophic. A bubble of the new vacuum state would nucleate somewhere in the universe and expand outward at the speed of light, erasing the current vacuum state and replacing it with something entirely different. The laws of physics inside the bubble would be different from the laws outside. The properties of particles would change. The forces would behave differently. Everything we know about chemistry, biology, and physics would be erased. This is not science fiction. Vacuum decay is a well-defined physical process predicted by quantum field theory. Now here is where the measured Higgs mass enters the story. The shape of the Higgs potential depends on its parameters, specifically on a quantity called the self-coupling of the Higgs, which describes how strongly the Higgs field interacts with itself. This self-coupling can be calculated from the Higgs mass and the Higgs vacuum expectation value. And the way it evolves with energy, how it changes as you probe the theory at higher and higher energies, determines whether the Higgs potential has a true minimum at the electroweak scale, or whether there is a deeper minimum lurking at higher energies. This evolution is described by what physicists call the renormalization group equations. You start with the measured values of the standard model parameters at low energies and calculate how they change as you extrapolate to higher and higher energies. When physicists performed this calculation with the measured Higgs mass of 125 billion electron volts, they found something striking. The Higgs self-coupling, which is positive at low energies, decreases as you go to higher energies. And at an energy scale of roughly 10 to the power of 10 to the power of 11 billion electron volts, a vast energy, far beyond any particle accelerator, the Higgs self-coupling appears to turn negative. A negative self-coupling means the Higgs potential no longer has a stable minimum at the electroweak scale. There would be a second, deeper minimum at enormous field values, enormously far away in field space. Our universe in this picture would be sitting in a false vacuum, a local minimum that is not the true minimum of the potential. The universe would be metastable, stable enough to persist for an extremely long time, but not truly stable. The calculation is sensitive to the precise values of the Higgs mass and the top quark mass. With current measurements, the universe sits very close to the boundary between stability and metastability, technically, within the metastable region, but not far from the stable region. The uncertainty in the top quark mass measurement is large enough that the universe might actually be in the stable region. We cannot be certain. But the central values point to metastability. How worried should we be? The answer depends on the tunneling rate, how quickly a bubble of the true vacuum would nucleate and begin expanding. Calculations suggest that the tunneling rate is extraordinarily slow. The expected lifetime of our metastable vacuum before tunneling occurs is many orders of magnitude longer than the current age of the universe. We are not in imminent danger, but the implications are profound nevertheless. If the universe is in a metastable vacuum, it means the current state of the universe is not the final, lowest energy state. It means that the laws of physics as we know them are not permanent. They are temporary. At some point, perhaps in an absurdly distant future, long after the last stars have burned out and the universe has reached heat death, a bubble of the true vacuum might nucleate, and the laws of physics inside that bubble would be different. What is more, this metastability is connected to the Higgs mass in a deep way. The Higgs mass of 125 billion electron volts places our universe very close to what physicists call the critical line between stable and metastable vacua, not firmly in either region right on the boundary. This is suspicious in the same way that the hierarchy problem is suspicious, not because it creates an immediate problem, but because it seems too precise to be a coincidence. The universe's vacuum appears to be tuned to be at or near the critical boundary. This might be coincidence. It might be a consequence of some deeper principle we have not yet understood. It might be pointing toward physics beyond the standard model that stabilizes the vacuum in a specific way. Some theorists have proposed that the near criticality of the Higgs mass is related to the hierarchy problem. In some models, particularly those invoking the multiverse, the probability distribution over possible Higgs masses might be peaked near the stability boundary. If most universes with different Higgs masses are either firmly stable or so unstable they decay before structure forms, then observers might preferentially find themselves in universes near the critical boundary. This is speculative, but it connects the hierarchy problem, vacuum stability, and the anthropic argument in an intriguing way. What is not speculative is the measurement itself. The universe, as best as we can determine with current data, is in a metastable vacuum. The laws of physics as we know them are not eternal. They sit in a local valley of a potential that has a deeper valley somewhere else in field space. And the depth of the valley we are in the shape of the Higgs potential is determined by the Higgs mass. The particle that gives everything its mass also determines the stability of the vacuum. It determines whether the universe is eternal or temporary. It determines whether the laws of physics are truly fundamental or merely local. That is not a small thing for one 125 billion electron volt particle to be responsible for. And it is why every measurement of the Higgs mass and Higgs couplings carries a weight beyond the immediate goal of testing the standard model. These measurements are charting the shape of the void. They are determining the stability of existence itself. Not the stability of anything as transient as a planet or a star or a civilization, but the stability of the vacuum state that makes atoms and chemistry and life possible. The Higgs boson is the guardian of the vacuum, and its mass tells us with extraordinary precision how secure that guardianship is. The discovery of the Higgs boson in 2012 did not end the story. In many ways, it began a new chapter. Before the discovery, physicists knew the Higgs mechanism existed. The success of the standard model required it. But the Higgs boson itself had never been directly observed. Now that it has been found, it can be studied. Its properties can be measured. Its behavior in collisions can be examined with precision. And the behavior of the Higgs boson is, in principle, an extraordinarily sensitive probe of physics beyond the standard model. Here is why. Every particle that interacts with the Higgs field, that is, every particle that derives its mass from the Higgs mechanism, interacts with the Higgs boson. The Higgs boson couples to particles in proportion to their mass. Heavy particles couple strongly. Light particles couple weakly. This precise relationship between coupling strength and mass is a specific, calculable prediction of the Standard Model. But if the Standard Model is incomplete, if there are new particles and new forces beyond what the theory contains, those new phenomena will generally affect the Higgs boson's couplings. A composite Higgs, for example, would have couplings that are slightly smaller than Standard Model predictions because the composite structure softens the interactions. Supersymmetric extensions would have multiple Higgs bosons with modified couplings. Extra-dimensional theories would introduce modifications from the Kaluza-Klein excitations. The Higgs boson, in short, is a magnifying glass, or more precisely, it is a microscope. It is an extraordinarily sensitive instrument for detecting the indirect influence of physics beyond the Standard Model, even if that physics involves particles too heavy to produce directly at the LHC. The current precision on Higgs couplings is roughly at the 10% level. The Higgs couples to the top quark, to the bottom quark, to the W and Z bosons, to the tau lepton in each case. Measurements from the LHC have confirmed that the coupling is roughly what the Standard Model predicts, to within about 10%. This already constrains beyond Standard Model physics significantly. Theories that predicted large deviations in Higgs couplings have been ruled out or severely constrained. Future colliders, particularly the proposed circular electron-positron colliders like the FCCE at CERN or the CEPC in China, would measure Higgs couplings at the fraction of a percent level. This extraordinary precision would be sensitive to new physics effects that are currently invisible. If the Higgs has compositeness at the percent level, if the Higgs mixes even slightly with some new scalar particle in a hidden sector, if the Higgs couplings are modified by quantum effects from heavy new particles, all of these would be detectable at the next generation of Higgs factories. This is the strategy that much of the physics community has coalesced around in the wake of the LHC's failure to find new particles. If new physics is there but heavier than the LHC can directly produce, it will still leave imprints, subtle modifications of known quantities, tiny deviations from Standard Model predictions. These deviations, if found, would be the first indication of what lies beyond our current understanding. It is a strategy of precision rather than discovery. Instead of producing new particles and identifying them directly, you make such precise measurements of known physics that the indirect presence of unknown physics becomes visible. The Higgs boson is the centerpiece of this strategy. Consider what a 1% deviation in the Higgs coupling to the bottom quark would mean. The Standard Model predicts a specific value. You measure it and find it is 1% smaller. That discrepancy, if real and statistically robust, would be telling you something. It would be saying that there is physics beyond the Standard Model that is modifying this coupling. The modification might come from heavy new particles that are too massive to produce at the LHC. It might come from the Higgs being composite at some scale above the LHC's reach. It might come from an extended Higgs sector with additional scalar particles that mix with the Standard Model Higgs. Whatever it is, it would be real. It would be a measurement, not a theoretical expectation, not an aesthetic preference, not a calculation of what should be. A measurement. There is something profound about this approach. The original Higgs searches at the LHC were looking for the dramatic. A new particle appearing in the data, a resonance, a spike in the production rate at a specific energy, a new object with a characteristic decay signature. Finding the Higgs in 2012 was exactly this kind of dramatic discovery. The next era of Higgs physics is different. It is the physics of precision, of fractions of a percent, of tiny deviations barely above the noise level. It requires not the most powerful machine, but the most controlled machine. Not the highest energy, but the cleanest environment. The LHC is not ideal for this. Proton-proton collisions are messy. Protons are composite objects, and their collisions produce a shower of particles that makes it difficult to measure the Higgs boson's properties with extreme precision. For precision Higgs physics, you want lepton collisions, electron-positron collisions, where the initial state is clean and precisely known. This is why proposals for new electron-positron colliders are receiving serious attention in the physics community. The FCCE, the CEPC, the International Linear Collider in Japan, each of these would be a Higgs factory, capable of producing millions of Higgs bosons in clean conditions and measuring their properties to percent level or sub-percent precision. None of these machines have been approved for construction yet. The decisions depend on international scientific priorities, funding, and political will. But the scientific case is compelling. If new physics exists at any energy scale below roughly 10 TeV, a Higgs factory should be able to see its effects in precision Higgs measurements. If no deviations are found at the fraction of a percent level, the constraints on beyond standard model physics would become extraordinarily tight, ruling out or severely constraining a vast range of theoretical possibilities. Either way, we learn something profound. Either we see the shadow of new physics in the Higgs couplings and follow that shadow to its source, or we find nothing, which would itself be deeply informative. It would tell us that whatever is beyond the standard model, it couples to the Higgs extraordinarily weakly, which would be surprising and require explanation. The Higgs boson that was supposed to complete the standard model is now being recruited as the instrument to break it open. The particle that was the answer to one question has become the sharpest tool for asking the next one. And the question it is asking is not subtle. Are we missing something? We are now more than a decade past the discovery of the Higgs boson. The Large Hadron Collider has smashed protons together at energies up to 13 trillion electron volts. It has collected data from billions upon billions of collisions. It has searched with extraordinary sophistication for every form of new physics that the most creative theoretical minds in the world have been able to imagine. And it has found the standard model. Nothing but the standard model. The Higgs boson was there, exactly where the theory said it would be. Its mass is 125.9 billion electron volts. Its couplings to other particles match standard model predictions to within current experimental uncertainties. It decays in the ways and at the rates the theory predicts. Every measurement is consistent, every prediction confirmed. No supersymmetric particles, no Kaluza-Klein gravitons, no extra-dimensional signatures, no top partners. No W or Z bosons, no leptoquarks, no excited quarks, no signs of new strong dynamics, no evidence for compositeness of the Higgs, no signals from any of the dozens of specific models that were proposed as solutions to the hierarchy problem, just the standard model, stretching further in its validity than anyone expected. What does this mean? The honest answer is that we do not know. There are several ways to interpret the silence of the LHC. One interpretation is that new physics exists, but at a higher energy scale than the LHC can reach. Perhaps the superpartners are at 5 TeV or 10 TeV. Perhaps the composite Higgs dynamics operate at 5 TeV. The LHC has explored up to about 2 to 3 TeV for most signatures and is approaching 4 to 5 TeV for some. There is territory above this that remains unexplored. New particles might be there, just beyond current reach. This interpretation is correct in the technical sense these possibilities have not been ruled out, but it comes at a cost. As the new physics is pushed to higher and higher energies, the hierarchy problem reappears. Remember, the whole point of natural solutions to the hierarchy problem was that new physics should appear just above the electroweak scale, near the TeV range. If new physics is instead at 5 or 10 TeV, then the Higgs mass is not entirely natural even with those new particles. A residual fine-tuning of roughly 1 part in 100 or 1 part in 1,000 creeps back in. This is sometimes called the little hierarchy problem. The hierarchy problem is not fully solved. It is mitigated but not eliminated, and the mitigated version is less compelling than the fully natural solution that motivated the original theories. A second interpretation is that the hierarchy problem is solved by a mechanism that the LHC cannot access, either because it operates at much higher energies, or because it involves physics that does not produce easily detectable signatures at a hadron collider. String theory, for example, could in principle provide a solution to the hierarchy problem that would not produce any signal at the LHC. If the extra dimensions of string theory are curled up at the Planck scale, or if the string scale is much higher than the TeV scale, the theory could stabilize the Higgs mass without producing any new particles within LHC reach. But then you are back to the question of naturalness. Why is the Higgs so much lighter than the string scale? And the answer may involve anthropic selection or some mechanism that operates at energies forever beyond experimental reach. A third interpretation, the most uncomfortable but the one that cannot be dismissed, is that the Higgs boson is fine-tuned. The universe simply has the parameters it has, and there is no deeper explanation. The electroweak scale is what it is, the Planck scale is what it is, and the ratio between them is an accident of the specific values the fundamental constants happen to take in our universe. Perhaps there are many universes with different values, and we find ourselves in one where matter can exist and form complex structures, because in the others, no one is there to ask why. This is the multiverse interpretation of the hierarchy problem. And it is deeply problematic for physics as a science, because it points toward an explanation that cannot be tested, a resolution that cannot be confirmed or refuted by any experiment. If the multiverse interpretation is correct, then the absence of new physics at the LHC is not surprising, it is expected. The Higgs mass was selected by anthropic constraints, not determined by a symmetry at the TeV scale. Looking for natural explanations at accessible energies was always a category error, but this conclusion, if accepted, would represent a profound change in the ambitions of physics. For 300 years, the program of fundamental physics has been to find deeper and deeper explanations for the observed properties of nature. Newton explained the motions of planets by deeper laws. Maxwell unified electricity and magnetism. Einstein showed that gravity was geometry. quantum mechanics revealed the wave-particle nature of matter. Each step went deeper, explained more, reduced the apparent arbitrariness of the world to greater and greater necessity. The anthropic interpretation of the hierarchy problem says, we have reached the end of that road. Some things cannot be explained by deeper laws. Some parameters were simply chosen by a cosmic lottery with no rule book. Most physicists are not ready to accept this, and they should not accept it too easily. Historically, premature resignation to apparent arbitrariness has always been wrong, but they cannot ignore it either. The LHC's silence makes the anthropic option harder to dismiss than it was 10 years ago. The field is at a crossroads. The path forward is not obvious, but there is a path forward, and it does not require giving up. The concept of naturalness deserves a deeper examination than we have given it so far, because naturalness is not just a technical criterion in theoretical physics. It is a philosophy, a statement about what kinds of explanations are acceptable in science. And the debate over whether naturalness has failed is a debate about the foundations of how we decide what theories of nature are worth pursuing. Here is the sharpest version of the argument for naturalness. Suppose you are told that the pressure inside a sealed container is exactly 1 atmosphere. You are told nothing else about the container. You would not be surprised. 1 atmosphere is a reasonable pressure for a sealed container that was sealed at sea level. But suppose you are told that the pressure is exactly the same as the atmospheric pressure outside the container to 17 decimal places. Suddenly, you would be suspicious. That kind of agreement is not an accident. Either the container has been connected to the outside atmosphere through some channel you do not know about, or someone deliberately set the pressure to match with extraordinary care. The extreme coincidence demands an explanation. This is the logic of naturalness as applied to the Higgs mass. The Higgs mass appears to agree with the combination of the bare mass and the quantum corrections to 34 significant figures. That kind of agreement, in the absence of any known mechanism causing it, is suspicious. It demands an explanation. The counterargument is equally sharp. The universe does not owe us explanations that satisfy our aesthetic sensibilities. The criterion of naturalness is a human judgment, not a law of physics. There is no theorem saying that parameters in the laws of nature must be technically natural. Perhaps the universe simply has fine-tuned parameters, and our discomfort with that fact tells us more about our psychological preference for tidy theories than about the structure of reality. This is a serious objection, and it is made more serious by an important historical example. There is at least one well-known parameter in physics that appears to be fine-tuned to an almost incomprehensible degree, where the only available explanation is anthropic. That parameter is the cosmological constant. The cosmological constant, the energy density of the vacuum that drives the accelerating expansion of the universe, is observed to have a value of roughly 10 to the minus 123 in Planck units. Quantum field theory predicts that it should be of order 1 in Planck units. The discrepancy is 123 orders of magnitude. The cosmological constant appears fine-tuned to a degree that makes the Higgs hierarchy problem look modest by comparison. The only argument that has any purchase on this problem is the anthropic one. Steven Weinberg showed in 1987 that the cosmological constant cannot be too large and positive, because then the universe would expand so rapidly that galaxies would never form. The observed value is consistent with this anthropic bound, and subsequent observations of the accelerating universe confirmed that the cosmological constant is non-zero and small, exactly in the range Weinberg's argument would predict. This is the most significant piece of evidence in favor of taking anthropic reasoning seriously in physics. It is not conclusive, but it is genuinely suggestive, and it forces an uncomfortable question. If the cosmological constant is fine-tuned for anthropic reasons, why not the Higgs mass too? The two cases are not identical. The connection between the Higgs mass and the possibility of observers is less direct than for the cosmological constant, but the parallel is unmistakable. There is a version of the anthropic argument for the Higgs mass. The Higgs vacuum expectation value controls the masses of the W and Z bosons. The W boson mass affects the rate of weak interactions in stars. Weak interactions govern the burning of hydrogen in stellar cores and the synthesis of heavier elements. The yields of carbon and oxygen in stars, the chemical basis of life, depend on the nuclear physics of stellar interiors, which depends on the Higgs mass, through a chain of dependencies that is indirect but real. An anthropic selection for a Higgs mass compatible with carbon-based observers constrains the mass to be not too different from its observed value. The argument is suggestive but not quantitatively precise. The anthropic window for the Higgs mass allows variations of perhaps a factor of a few, not a single value. This is different from the cosmological constant, where the window is extraordinarily tight, but the argument is coherent. And in a multiverse context, where many universes exist with different values of the Higgs mass, anthropic selection would explain why we find ourselves with this particular value without any natural mechanism required. The physics community is split on this. Some physicists, particularly a generation that has grown up with the LHC's null results, are more willing to entertain anthropic explanations. Others resist vigorously. The resistance is not irrational. Naturalness has been productive for decades. Abandoning it too soon would be a mistake, but the possibility cannot be dismissed, and it sits at the center of the deepest methodological debate in fundamental physics in a generation. What is the correct criterion for judging theories of nature if naturalness has failed? This question does not yet have a consensus answer. Some physicists argue for a revised criterion called ultraviolet sensitivity, asking not whether a theory is natural, but whether it is sensitive to the structure of physics at very high energies in ways that are observable in principle. Others argue for predictive power as the primary criterion, asking which theories make the most specific testable predictions about phenomena we can measure. Still others are exploring mathematical consistency criteria, asking which theories can be ultraviolet completed in a consistent framework and which cannot. None of these replacements for naturalness has the same clarity or operational power. The field is genuinely groping for a new guiding principle. And that groping is a healthy sign of science at the frontier, uncomfortable, uncertain, alive with the tension between what we know and what we do not. The Higgs boson's mass is at the center of this tension. It is not just a number to be measured. It is a question about how the universe works and how we come to understand it. Physics has been here before. Not here exactly, the specific problem of the hierarchy problem is unique to this moment in history, but in a situation where the most powerful available experiments find nothing new. where theoretical ideas are running ahead of data, where the meaning of the data is not yet clear. It has always resolved, not always quickly, and not always in the direction that was expected, but resolution came. The history of physics is littered with examples of null results that eventually yielded to new ideas or new experiments. The Michelson-Morley experiment failed to detect the luminiferous ether, the medium through which light was supposed to propagate, and its null result was perplexing for years until Einstein's special relativity made the ether unnecessary. The search for the medium had failed, but the failure pointed towards something deeper and more beautiful. The current situation is not hopeless. It is just hard. The Large Hadron Collider is currently being upgraded to become the high luminosity LHC, which will increase the number of collisions by a factor of 5 to 10. This will not increase the maximum energy of the collisions, but it will dramatically increase the statistical sensitivity to rare processes. New particles that are too massive to produce frequently might still be produced occasionally, and with more data, occasional production becomes detectable. The high luminosity LHC will operate until at least the late 2030s, collecting a dataset 20 times larger than what currently exists. This is not nothing. Rare processes matter. The Higgs boson itself was discovered with comparatively few events, only a handful of candidates in each decay channel. With the high luminosity LHC, the measurement of Higgs couplings will improve significantly. If deviations from standard model predictions are at the few percent level, the high luminosity LHC should have sufficient sensitivity to see them. Beyond the LHC, proposals for higher energy colliders are being actively debated. CERN has proposed the Future Circular Collider, an enormous machine that would first operate as an electron-positron Higgs factory, and later as a proton-proton collider at 100 TeV, roughly 7 times the energy of the current LHC. At 100 TeV, entirely new mass ranges would become accessible. If superpartners exist at 10 to 20 TeV, a 100 TeV collider could produce them. If the compositeness scale of the Higgs is at 10 TeV, a 100 TeV collider would probe it directly. China has proposed the Circular Electron-Positron Collider, which would serve as a precision Higgs factory before potentially being upgraded to a higher energy proton collider. Japan has proposed the International Linear Collider, a straight-line electron-positron machine designed specifically for precision Higgs measurements. Each of these machines represents a massive investment of resources and political will. None have been approved for construction. But the scientific case is being made, and the decisions will be among the most consequential in the history of fundamental physics. There are also other experiments that do not require building larger accelerators. Dark matter experiments are growing steadily more sensitive. The current generation of liquid xenon detectors, LZ, Xeno-NNT, Pandarex are probing interactions between dark matter and ordinary matter at levels that are several orders of magnitude more sensitive than the original searches. If dark matter consists of WIMPs with weak-scale masses and couplings, these experiments should either find a signal or rule out the entire WIMP hypothesis within the next decade. Neutrino experiments are addressing the question of CP violation in the neutrino sector, whether neutrinos and antineutrinos behave differently in their oscillations. If they do, it could explain why the universe is made of matter rather than antimatter. Dune and Hyperkamiokand are the flagship experiments for this search, with Dune currently under construction in the United States and Hyperkamiokand in Japan. Gravitational wave observatories are opening an entirely new window on extreme physics. The LIGO and Virgo detectors have already observed dozens of black hole and neutron star mergers. Future detectors, the Einstein Telescope in Europe, Cosmic Explorer in the United States, LISA in space, will be sensitive to gravitational waves from the early universe, from cosmological phase transitions, and from exotic objects like primordial black holes. These signals could carry information about physics far beyond the standard model, at energies inaccessible to any particle collider. And precision measurements of all kinds of atomic structure, of rare particle decays, of fundamental constants, continue to constrain theories of new physics with increasing sensitivity. Sometimes the first hint of something new comes not from the most powerful experiment, but from the most precise one. The search for what lies beyond the Higgs boson's unexplained mass is not over. It has barely begun. But there is something else worth saying here, something about the nature of the problem itself, and what it tells us about where we are in the project of understanding the universe. The hierarchy problem is, at its core, a problem about scales. It asks, why are there two such different scales of energy in the laws of physics, the electroweak scale where the Higgs lives, and the Planck scale where gravity becomes important, separated by 16 orders of magnitude? Why does the universe have this structure? This is not a question with an obvious answer. It is not even clear that it has an answer in the conventional scientific sense. It might be one of those questions that, as we understand more, reveals itself to be asking something different from what we originally thought. Every great advance in physics has changed the questions. When Newton unified celestial and terrestrial mechanics, the question, why do planets move in ellipses? Dissolved, it became not a question about planets, but a consequence of the inverse square law of gravity. When quantum mechanics arrived, the question, why do electrons orbit the nucleus without spiraling in? Dissolved, it became not a question about stability, but a consequence of the wave nature of matter. Perhaps the hierarchy problem will dissolve too. Perhaps the question, why is the Higgs mass so much smaller than the Planck scale, will turn out to be asking something we have not yet framed correctly. Perhaps the answer will reveal not just the missing physics, but a new way of thinking about what physics is asking. That is not a prediction. It is a hope grounded in history, and it is the spirit in which the search continues. Let us come back to where we started, to the number that might be the most important in the universe. But first, let me reflect on what kind of problem the hierarchy problem really is, because we have spent most of this journey looking at it from inside the physics, the technical machinery of quantum corrections, the successes and failures of supersymmetry, the precision measurements and their implications. It is worth stepping back and appreciating what kind of question this is at a more fundamental level. Physics, throughout its history, has been driven by two kinds of questions. The first kind asks, what are the rules? What equations govern the behavior of nature? These are the questions that led to Newton's laws, to Maxwell's equations, to general relativity, to quantum mechanics. They are questions about the dynamics of the universe, about what happens and why. The second kind of question is different and in some ways harder. It asks, why are the rules the way they are? Why does gravity fall off as the square of the distance rather than the cube? Why are there 3 generations of quarks and leptons? Why does the electromagnetic force have the particular strength it has? These are questions about the parameters of the rules, not the rules themselves. For most of the history of physics, the second kind of question was not considered a proper scientific question. Parameters were measured, not explained. The constants of nature were what they were, and it was not the job of physics to explain why they had particular values. That seemed like metaphysics. But the Standard Model changed this, because the Standard Model is so powerful and so precise that it has made us hungry for deeper explanations. We can calculate everything so well that the things we cannot calculate stand out like sore thumbs. The parameters of the Standard Model, the masses of the quarks, the strength of the forces, the Higgs mass are measured inputs, not derived outputs. The theory does not explain them. And physicists have come to believe, based on experience and analogy, that a truly fundamental theory would derive them from something deeper. The hierarchy problem is the clearest case where a Standard Model parameter screams for explanation. Not just because it seems fine-tuned in the abstract, but because the fine-tuning is quantifiable, precise, and connected to fundamental scales in physics in a way that ordinary parameter tuning is not. The Higgs mass is not just accidentally small. It is small in a way that requires extraordinary cancellation between quantities that, by rights, have no reason to be related. That is the sharpest form of the problem, and it is the form that has driven 4 decades of theoretical effort. Now, what does it mean that we have not found the answer yet? It means one of several things, and the honest answer is that we do not yet know which. It might mean that the answer is just around the corner. That the next run of the LHC, or the high luminosity LHC, or a future higher energy collider, will finally produce the evidence for the mechanism that stabilizes the Higgs mass. The supersymmetric particles might be there, just heavier than expected. The composite dynamics might leave their imprint in precision Higgs measurements at a level we can detect. The next generation of experiments might find the answer. It might mean that the answer is there, but not accessible to any accelerator we can build in the foreseeable future. The new physics might be at 100 TeV, or 1000 TeV, or higher. The hierarchy problem would remain open until a different kind of experiment, perhaps precision measurements of Higgs properties, perhaps cosmological observations, perhaps something we have not thought of reveals the mechanism indirectly. It might mean that the concept of naturalness, which has guided the search for 40 years, is simply wrong as a guide to nature. The universe might be fine-tuned, perhaps by anthropic selection in a multiverse, and there is no mechanism to find. The search for natural solutions would have been looking in the wrong direction all along, or it might mean that the question itself is being asked in the wrong way. That the hierarchy problem, as we have formulated it, reflects a conceptual confusion about the relationship between low energy and high energy physics, that a deeper understanding of what quantum field theory is actually telling us about the nature of the vacuum, about the relationship between different energy scales, about what renormalization means physically, will dissolve the problem rather than solve it. This last possibility is the most radical and the hardest to evaluate. It would require a conceptual revolution, not just a new particle or a new symmetry. It would mean going back to foundations and asking whether the framework we have been working within perturbative quantum field theory, the Standard Model of renormalization, the standard interpretation of what virtual particles and quantum corrections mean, is actually the right framework for asking questions about the hierarchy. Some physicists are beginning to explore this direction. Arguments have been made that the hierarchy problem, properly understood, is not about fine-tuning of parameters, but about the structure of the theory near the Planck scale, and that a proper theory of quantum gravity might simply not exhibit the dangerous ultraviolet sensitivity that makes the hierarchy problem look so severe. In a theory of quantum gravity, spacetime itself is quantized at the Planck scale. The concept of virtual particles with Planck scale momenta, which is the source of the enormous corrections to the Higgs mass, may not even be well defined. The problem might be an artifact of applying a low-energy effective theory, quantum field theory, in a regime where it does not apply. This is speculative. But it is not unreasonable to suspect that the hierarchy problem, which lives precisely at the interface between quantum field theory and quantum gravity, might require a theory of quantum gravity to resolve. And we do not yet have a satisfactory theory of quantum gravity. We are, in other words, confronting the boundaries of our theoretical framework at the same time as we confront the boundaries of our experimental reach. This is unusual. In most of the history of physics, the experimental frontier and the theoretical frontier were separated. You had a working theory that was outrunning experiment, or experiments revealing phenomena that the theory could not yet explain. The current situation is more symmetric. Theory and experiment are both running up against their limits at the same time. The LHC has reached the limit of what is economically and technically feasible with current technology. The standard model has revealed its own incompleteness in a way that points toward physics beyond current theoretical frameworks. This convergence is uncomfortable. But it is also potentially enormously exciting, because when theory and experiment both run out at the same time, what is needed is not incremental progress. What is needed is a new idea, a genuinely new way of thinking about the problem. Not more supersymmetric particles or more extra dimensions or more composite models, variations on existing themes, but something fundamentally different. The kind of shift that happened when quantum mechanics replaced classical mechanics, or when general relativity replaced Newtonian gravity. We cannot predict what that new idea will be. By definition, a genuinely new idea cannot be anticipated from within the existing framework, but we can know that it is needed, and knowing that is something. The hierarchy problem is a sign pointing at a door. We do not know what is behind the door. We do not even know exactly where the door is, but we know it exists. And that is more than physicists knew 100 years ago, before the standard model was built, when the universe's fundamental structure was entirely opaque. We have come a long way. We have further to go. 125.9 billion electron volts, the mass of the Higgs boson, the number that should not be what it is and yet is. We have traveled a long way tonight. We have gone from the surface of the problem, the discovery of a particle predicted 50 years before its detection, down through layers of increasing depth and mystery. We have seen how the Higgs field gives particles their mass, and how the Higgs boson's own mass refuses to be explained by the same mechanism. We have walked through the hierarchy problem and understood in real terms why physicists find it so unsettling. We have explored the proposed solution's supersymmetry, extra dimensions, composite models, and grappled honestly with the fact that the most powerful particle accelerator ever built has found none of them. We have confronted the possibility that the fine-tuning is real. That the universe is simply arranged this way, and there is no mechanism to discover, no symmetry to uncover, no deeper principle to find. That the anthropic principle might be the closest thing to an explanation that exists, and we have refused to accept that conclusion prematurely. Because the history of physics says that apparent arbitrariness is a symptom, not a diagnosis. It says that when the numbers do not make sense, there is always a deeper reason waiting to be found. The Higgs boson sits at the intersection of everything we know and everything we do not. It is the last predicted particle of the Standard Model, the capstone of 50 years of theoretical and experimental work. And it is simultaneously the first crack in that model, the particle whose properties refuse to be explained by the theory that contains it, pointing outward towards something larger and deeper. It is, in this sense, the perfect symbol for where physics is right now. We have built a theory of extraordinary power and precision, a theory that predicts the behavior of matter at the most fundamental level we can access. A theory that works with a degree of accuracy that no other scientific framework has ever matched. And we know with equal certainty that it is not complete, that it is missing something, that somewhere beyond its edges, in the darkness beyond what our best instruments can currently illuminate, there is more. The Higgs boson is the flashlight pointing into that darkness. Not because it is broken, it is not broken. The Higgs boson is behaving exactly as the Standard Model predicts. But because the very fact of its existence, its measured mass, its inexplicable lightness in the face of what should be enormous quantum corrections, is telling us something, insistently, persistently, something is wrong with our picture, something is missing. Think about what we have accomplished to even pose this problem. The Higgs boson is not visible to any telescope. It cannot be seen with any microscope. It has no color, no permanent charge, no long-term existence. It decays within 10 to the power of minus 22 seconds of being created. It is one of the most ephemeral objects in the known universe. And yet we know it exists, we know its mass, we know its couplings to other particles, we know the decay channels through which it disappears. All of this known, measured, confirmed. We did this with mathematics and ingenuity and billion-dollar machines buried beneath the Swiss-French border. We did this by following the logic of symmetry and field theory and quantum mechanics wherever it led. We did this by building arguments so abstract and so mathematical that almost no one outside a small community of physicists can fully follow them, and then building experiments that translated those abstract arguments into observable events. This is what humans can do. This is what curiosity and rigor and the scientific method can achieve, and it is not finished. The particle that should not exist, the Higgs boson, impossibly light in the face of the corrections that should destroy its lightness, is still talking to us. Every collision at the LHC that produces a Higgs boson is another whisper from the universe about what it is made of at the deepest level. Every measurement of a Higgs coupling is another constraint on the space of theories that could explain what we observe. We do not yet have the final answer. The solution to the hierarchy problem remains unknown. The nature of whatever lies beyond the Standard Model, whether it is supersymmetry, extra dimensions, compositeness, or something no one has yet imagined, remains to be discovered. But the question is clearly posed. The instruments are being built. The data is accumulating. The theories are being tested against experiment with a rigor that would have seemed impossible just a generation ago. The universe has one more secret to give up about what matter really is and why it has the form it takes. We have not found it yet, but we know where to look. We know what the clue is. We know what question to ask. It begins with a number: 125.9 billion electron volts, the mass that should not be but is. Sleep well tonight knowing that somewhere beneath a mountain in Switzerland, protons are colliding at nearly the speed of light, and the universe is being asked, one collision at a time, to explain itself. The answer is coming. We just have to keep listening. Good night.